This is video 4 of Unit 1. In this video, we'll talk about the mole. And not only will we mention furry animals, but the more important concept of the mole, which relates to chemistry and counting atoms. So, the mole is actually a number in chemistry that's a unit used to count atoms. So because atoms are so tiny, we need a special number to help us count them. And it's related to the idea of a dozen. We all know that a dozen stands for the number 12. We can use a dozen for produce, so a dozen eggs would be 12 eggs. A dozen atoms would be 12 atoms. And similarly, we define a quantity called the mole to simply stand for a certain number. Now the number is really big. The number is 6.02 times 10 to the 23rd. And this number written out has quite a few zeros, 21 zeros. And so the number is quite big. That's because atoms are quite small. Now, to help you visualize how big this number is, we can try to visualize a few concepts. So say if you had a mole of dollar bills, and you got to spend 1 billion of them every single second. How long would it take you to spend the whole mole of dollar bills? And the answer is pretty astounding. It would take you 1.9 million years. Now that's spending 1 billion every second. So you would be buying an island or two probably every second, and you'll run out of islands on Earth pretty quick. So it's pretty astounding. Now the second question says, what if you had a mole of marbles and you had to put them somewhere? How much room would they take up? The answer is also pretty astounding. They would actually cover the Earth to a depth of 50 miles all around the Earth, which is pretty astounding. Marbles about this size. And the third question, the more important one, is can Mr. Zinovchik drink a mole of water molecules? So we'll have to wait till class time, and we'll find out if we can demonstrate the drinking of a mole of water molecules. So this allows you to see how tiny atoms are and how big this number has to be to have a certain amount of these atoms. The guy that came up with this idea is Amedeo Avogadro, a fine-looking young man. So the exact number is actually, if you want it to 7 decimal places, here it is. But we will be fine with just using 3 significant figures for most of our calculations. 6.02 times 10 to the 23rd. Now, Mole Day is actually celebrated every year by chemists and students on October 23rd. So the 10th month, the 23rd day. So next month, Mole Day is coming up. Hopefully you will join us for the festivities. Festivities actually begin at 6 in the morning. Actually, we shoot off the confetti at just 2 minutes past the hour. We get there at around 6, and we celebrate until 6:02 the next morning. So it's actually a 24-hour celebration. And so hopefully you can join us this year for Mole Day. So essentially what we're going to do with this definition is do problems, do conversion problems. And I should say that a mole is roughly an amount of atoms that you can work with. It's a perfect amount of atoms you can work with. So say if you had 1 mole of some sort of element, you can definitely see it, and it'll most of the time fit in the palm of your hand, a mole. And that it's a really comfortable number, so we can work with these atoms in the laboratory. So the question is, how many aluminum atoms in 2.5 moles of aluminum? So do a little conversion problem. Get that out of the way. And we've got 2.5. Go ahead and begin just like we've converted with dimensional analysis earlier. 2.5, put down the unit as moles. You can put down aluminum if you'd like, or it won't matter. As you'll see, the moles will work the same way for any element. Multiply by a conversion factor, so a mole will go down here since it has to cancel out, and then atoms will go up here. Now, our relationship, our conversion factor between atoms and moles, is that 1 mole is that big number, 6.02 times 10 to the 23rd atoms. So essentially what you'll have to do is multiply 2.5 by 6.02 times 10 to the 23rd. If you want, you can simply multiply 2.5 by 6.02, which will give you 15.05, and then you can add the times 10 to the 23rd. Or if you want to express it as 1.5, and then 1, because we want actually we want two sig figs, so just 1.5. So what I've done is I've moved the decimal left here, so I'll have to move this to the right up to the 24th. So 1.5 times 10 to the 24th. Don't forget the units. In this case, the units will be atoms. So if you have 2.5 moles of aluminum, here is how many atoms of aluminum you'll have. You'll actually have more than a few aluminum cans if you had 2.5 moles. Probably have a good stack of aluminum cans with that many atoms. So hopefully this makes sense. Go ahead and pause the video, try the practice problem yourself. Same idea except with zinc. Now let's talk about what else the mole represents. The decimal number on the periodic table actually tells us two things. Remember, the decimal number is the mass. It's this number right here. And it tells us the mass of one atom, called the atomic mass. So chlorine, for example, has a mass of 35.453 AMU, atomic mass units, sometimes also called just U. And the second thing it tells us is the molar mass, what's called the molar mass. Molar mass is the mass of a mole of atoms. So it says if you had a mole of these, if you had 6.02 times 10 to the 23rd of these chlorine atoms, they would weigh exactly this many grams. And that's the whole point of using this number as the definition, so that the atomic mass and the molar mass match up. So now this definition is going to be extremely important for us. In fact, this is one of the most important numbers on the periodic table because it allows you to use these chemicals in the laboratory, weigh them, measure them, and so forth. So we will actually work with this number next. And we'll do a few example problems. The example problem here says convert 25.5 grams of carbon to moles of carbon. Now if you take a look at carbon on the periodic table, carbon is element number 6, and its atomic mass is 12.01. So now we realize that this is also 12.01 grams in 1 mole. So this will actually now be our conversion factor. Let's go ahead and begin the problem as we always do. 25.5 grams of carbon. In this case, I would recommend that you label which element you're dealing with because each element will have a different mass from the periodic table. So grams of carbon down below, moles of carbon up above. The relationship here now is 1 mole of carbon is 12.01 grams of carbon. So 1 mole is 12.01 grams. And to do the calculation, it's as simple as dividing 25.5 by 12.01, which gives you 2.12. In this case, it is moles of carbon. So hopefully that made sense. Go ahead and try a problem on your own. Pause the video, try this one with lithium. Now to summarize, what we've given you is 2 conversion factors. We've given you the conversion factor between moles and atoms. This one here, we said 1 mole is 6.02 times 10 to the 23rd atoms. And this will be true for any element. All elements are defined to have this many atoms in a mole, because we can even say a mole of apples is this many apples. A mole is a counting number that applies to anything. And then we also, the other conversion factor is a mole to grams. Now this will be specific for that element. So carbon has a mass of 12.01. If you had chlorine, chlorine would have a mass of 35.45. You'll have different masses depending on the element that you're looking at. So the right side will be the same always, the left side will not be the same for every element. And here the statement moles are in the middle means if you want to convert, say, from grams of an element to atoms of that same element, you'll have to go through moles because moles are in the middle. In fact, we're going to try just that. Here's the example that asks how many atoms are there in 1.5 or 1.1 grams of iron. Now let's go ahead and find iron on the periodic table. We'll need its atomic mass. Iron is element number 26, and its atomic mass should be somewhere in the 50s. 5585. I'll consult your periodic table for this. 5585. This will be its atomic mass. Also its molar mass. Okay, this will be a two-step problem because what we'll have to do is go from grams into moles and then from moles into atoms, because moles are in the middle. Alright, let's go ahead and set it up. So we got 1.1 grams of iron. Go ahead and label it as iron. This will be a two-step, so let's go ahead and convert it with two conversion factors. At the bottom, the first step will go grams of iron because it has to cancel out. And since moles are in the middle, we will first convert to moles. Then we'll go from moles, means moles goes down here, to atoms. Now notice that usually I don't put moles of iron because a mole won't matter, but we'll go ahead and put atoms of iron in the end. Now to put the conversion factors in, a mole to gram conversion is given to you in the atomic mass. So a mole of iron is 55.85 grams of iron. And a mole of iron is 6.02 times 10 to the 23rd atoms of iron. Go ahead and do this calculation. You'll do 1.1 divided by 5585 times 6.02, which gives you 0.1186 times 10 to the 23rd. Now, first of all, we want two significant figures, and second of all, I want to write it as 1.1. In this case, the 8 rounds the 1 up to a 2, so I'll do 1.2, and then times 10 to this. Since I went to the right, I'm going to go to the left once, times 10 to the 22nd. And go ahead and label it as atoms of iron. So if you have about a gram of iron, now a gram of iron, if you have a big paper clip, that's about a gram, if it's a big paper clip, about a gram of iron in that paper clip, which means you have 1.2 times 10 to the 22nd atoms, which is really neat because now you can actually count how many atoms there are in any item that you wish. You can dare a friend to count how many atoms there are in some sort of item, and then you can impress them with a little add grams to moles to atoms calculation, and we encourage that sort of behavior. Here's a problem for you to try. Go ahead and pause the video, try this problem. And then we're going to finish up talking about the same idea with compounds. Now a compound, remember, is made of different elements, 2 or more elements. It's a pure substance, but it's made of elements that are chemically bonded. So the most famous example is H2O. That's a compound because it has hydrogen and oxygen in a ratio of 2 to 1. Carbon dioxide is another famous, probably the second famous compound. Sodium chloride, which is table salt, is probably the third most famous compound. And this is the fourth most famous compound. You may not recognize it, or you may recognize this is good old sugar. And this is actually table sugar. There are different versions of sugar. This is table sugar, just like there are different types of salts out there. So each of these compounds, you can do the same thing. You can actually convert to moles, because moles apply to atoms, and these molecules are made from atoms. You'll see that the same concept will be applied. So let's go ahead and define what a molecule is to make sure we have this idea. A molecule is an individual unit of a compound. So if you have a compound, and say if you have a bunch of water, this is actually water, this is ice because it's in a very ordered arrangement, means it's in the solid state. And if you take 1 unit of that ice, of the molecular mixture, you'll actually get what's called a molecule. So a molecule is an individual unit of a compound, and of a special type of compound. So we can ask this question now: what is the molar mass of H2O? Now, just because water is made of hydrogen and oxygen, what we can simply do is take a look at hydrogen on the periodic table, take a look at oxygen on the periodic table, and find their molar masses, 101 for hydrogen and 1600 for oxygen. Incidentally, I should say that our periodic table has just 2 decimal places past the point, and that will suffice. That will be enough for all our calculations. You don't have to go any further unless you're doing some sort of precise calculations. So Now we have two hydrogens, which means we'll have to double this number and then add it to this number. And then we'll get the molar mass. So it's simple. So you got 1.01 plus 1.01 plus 16.00, which gives you exactly 18.02 is the molar mass of water. Now, the units for this, for molar mass, because molar mass is the mass of a mole, so it's actually grams per mole will be the units. You could put just grams, that would be correct, but molar mass is defined as grams per mole, because you literally have 1 mole of this compound that weighs 18.02 grams. Good? Now the question here, the follow-up question is, how about the mass of 1 molecule of water? Now, it's actually going to be the same. It's going to be 18.02, because remember we said that this number on the periodic table measures the mass of 1 atom and the mass of a mole of atoms. So if you think of a compound, same idea applies. This is the mass of a mole of that compound, and this is the mass of 1 molecule of that compound, except the units here would be given as AMU. This is actually called molecular mass. For an atom, it would be atomic mass. For a compound, it'll be molecular mass. This is sometimes also referred to as formula mass. So the mass of a formula, or of the formula. Now, what if you said, well, I need to know the mass of a water molecule in grams? That would be really, really tiny. Remember, the mass of a proton, we said, is 10 to the negative 24th grams, which means if you have a carbon atom, or an oxygen atom in this case, has 8 protons, so it's going to be extremely tiny. But you could do that. And the way you would do it is you realize that this is per mole, grams per mole, and what you could do is you could take your 1802 grams in 1 mole and then convert from moles to atoms. So you'll put the moles up here, so it cancels out. You'll put the atoms down here, and a mole is 6.02 times 10 to the 23rd atoms. You end up dividing 1802 by how many atoms you have, and you'll actually get the mass of 1 single molecule of water. So you can definitely do it using this conversion. All right, let's go ahead and finish up with a few examples. Here it says how many moles of CO2 are in 39.7 grams of CO2. So what we're going to do is do a conversion problem like we've done before. So put 39.7 grams of CO2, multiply by a conversion factor, and we'll have to go from grams of CO2 into moles of CO2. The relationship is from the periodic table. So a mole, how many grams? Well, in this case, we have to add up the mass of carbon and 2 oxygens. The mass of carbon from the periodic table, if you take a look at 12.01, and the mass of oxygen is actually 16, and there are 2 of them, since CO2 is 2 oxygen atoms. The subscript refers to how many of the element before it. And if you do this correct, we should end up with 44.01 grams in a mole. So you do 44.01, and then to calculate, you do 39.7 divided by 44.01, and 3 significant figures gives us 0.902. This would be moles of CO2. So exactly the same thing we've done with atoms, you can apply it to compounds like CO2. Do a problem, similar problem with water as a practice problem, and then let's finish up with this one. What is the mass of 2.5 moles of calcium hydroxide? Same idea, except now we're going from moles to grams. So we've got 2.5 moles of calcium hydroxide. Now, we'll teach you how to name these compounds, but right now I want you to see that the 2 applies to everything in the parentheses. So in fact, what you have is you have 2 oxygens and you have 2 hydrogens, and you have only 1 calcium, because the 2 applies only to what's in the parentheses. You ask yourself, well, why didn't they just write it out like this? And there's a reason for it. They want to show that the O and the H are bonded individually together in a certain way. So that's why it's written that way. But we'll do the same thing in our conversion factor. We'll put moles down here of calcium hydroxide. This item here, this compound unit, is called hydroxide because it has hydrogen and oxygen. And so we'll put grams of calcium hydroxide above. Now, if you take a look at the periodic table, go and find calcium. Calcium should have a mass of 4008. I got 2 oxygens, which is 1600, and I got 2 hydrogens, which is 101. So total that up. 8 plus 2 is 10, plus 1 more, that's a 1. We got 14, and 5, 6, 7, so 7410. So 74.10 grams of calcium hydroxide in 1 mole of calcium hydroxide. And simply multiply 2.5 by 7410, and 2 significant figures gives us, the whole thing says 185.25. Remember, you'll go by the number of starting significant figures, so we simply round this up to 190 grams of calcium hydroxide. Okay, so hopefully this makes sense. Go ahead and try the last problem on your own, and then we'll see you in class.